We are live. All right. Day 7 of learning linear algebra from scratch with nothing but ChatGPT as my tutor slash professor slash teacher. Let's see how it goes. I am really in a good place with this. I did well on my first test. I got a 90%. I posted a quick little video this morning just recapping that. And it's nice seeing more people commenting, more people following me on this journey to see what are the capabilities of AI to be a teacher for someone who hasn't learned something as complex as linear algebra, to actually learn it from scratch. I have been working in education for a long time, so I'd like to think I know what a model student behavior should look like. Ideally, I should be spending some time on homework, but I'm not. I'm just spending an hour per day for 30 days to try to learn linear algebra at the level of a course at MIT or Harvard or Princeton or some elite university. So without further ado, I don't have a ton of time today. I'm going to have to cut this a little bit shorter than an hour, but I want to go into the next lesson, which is lesson 7. And you'll see lesson 7. I'm going to X this out. Lesson 7 is time for the unit 2 test. So I have this new unit 2. I'm going to just read about this unit overall. Vector spaces and linear transformations. This is a longer unit than the first unit, it would appear. It's 9 days compared to the 6 for the first unit. Now we get the formal theory of vector spaces and subspaces, building on the computational foundation of Unit 1. Here the course becomes more rigorous. Let's go. You will learn the abstract language that underpins all of linear algebra. Vectors, span, basis, dimension. We touched on that in the first unit, while still connecting to concrete examples like solution spaces of, can't really see what that is, or a column space of a matrix, I presume. We also introduce linear transformations in general. Mastering this unit gives you the mathematical vocabulary. So vocabulary is going to be important here. I need to improve the Chrome extension that I coded to help me learn all this stuff. I'll try to find some time to do that tonight if I don't fall asleep early, but we'll see. And yeah, this should be really interesting. So the first lesson is defining the definition of a vector space and subspace. So it says I should understand the definition of a vector space over something and recognize examples. So this isn't very clear what it's all talking about. I'll just say, give me the lesson plan for lesson 1 of unit 2. You know what, I actually don't want to copy it. I want to use this feature in ChatGPT, which a lot of people don't know about. You can highlight something and then say that. I'm ready. It says this is lesson 6, vector spaces and subspaces. That's already kind of awkward because I don't think it is lesson 6. This is day 7. Let me just confirm that I'm not making a counting error here. Unit 1 had 5, 6 lessons. Yeah, this is lesson 7. Definition of a vector space and subspace. Hopefully I got that. I'm going to copy it here. And what I'm going to do is I'm also going to put this into another chat. Let's do it for O3 mini high. Sort of new chat for that. Give me a linear algebra lesson for this material. Make it equivalent to the rigor of an MIT linear algebra class. All right. This main chat I found to actually be better than just about anything else. It works quite well. But I like to always cross-check. I've learned it's very useful to cross-check what I'm learning with other AI models just to make sure that I don't miss anything important. By the end of this lesson, you'll be able to define what a vector space is over a set of real numbers. That's what this R thing means. Recognize valid examples of vector spaces like an n-dimensional space, spaces of functions, matrices, polynomials. Determine whether a given set is a subspace of a vector space by checking the 0 vector is included, if it's closed under vector addition, or if it's closed under scalar multiplication. Cool. So I'm just going to write some key terms here. It seems like, again, linear algebra is getting very key term heavy. Vocabulary is going to be a big part of this unit, so I need to really hone in on that because it's hard in just an hour to master vocabulary. It's better if you do some spaced repetition throughout the day. Building an app so that I do that just while I'm browsing my computer. But let's go ahead now. I want to go vector space. I want valid examples of vector space. I don't need that. I'm just going to go subspace. All right, what is a vector space? A vector space over R is a set of objects called vectors equipped with. So it's a set of vectors with vector addition and scalar multiplication that satisfy 10 specific axioms. Whoa, 10. Which we'll simplify shortly. So typical vector spaces are an n-dimensional space, a set of polynomials. I'm curious how that is a vector space. Set of all continuous functions, C, from 0 to 1. A set of m by n matrices. What all these have in common is that you can add their elements and scale them, and the results still live in the space. So I can take all the elements of each of these things and scale them or add them, and they still live in the space. I'll be honest, I don't understand that fully. The vector space axioms. These are the rules that the space must obey. You don't need to memorize all 10 right now, but understand the themes. Closure under addition, commutativity. So this is interesting. It said there were 10 rules. I'm wondering why they're all only 7 right here. You don't need to memorize all 10 right now, but understand the themes. So I'm just going to write the 10 axioms of, what is it? The 10 axioms of a vector space. 10 rules of a vector space. So it's closed under addition. I need to remember what this symbol means. What does this symbol mean? Other useful symbols like this. So there's commutativity. One vector u plus another vector v is equal to the same thing as v plus u. That makes sense. They're closed under addition. U plus v is contained within, I guess the v is the vector space. I think that's what it means, is contained in. Let's see what it says it means. Is an element of. Okay, cool. I'm going to write this down. Is an element of. Or belongs to. Okay. X is a vector in R squared. Other important symbols. Is a subset of. Okay. This is good. Is a subset of. It really is like learning a new language, all this linear algebra stuff. It's pretty crazy. Then implies and if and only if. I didn't even know that. I've just been using that symbol because it's kind of a nice thing. Implies. See, I was using it above. And I guess there are 2 lines next to the arrow. If and only if. I know this is all written here, but it's, helpful to write stuff down for committing it to memory. This is a vector. I knew that. You write an arrow on top of a letter. Special matrices, the 0 scalar, the 0 vector, the identity matrix, span. All linear combinations of a vector, okay? Span of V1 and V2. all linear combinations. Okay, I think that makes sense. Dim V is the dimension of the vector space. I think this is going to be helpful, just having this off the bat. Rank and nullity, I get that. Might as well write it though. Rank, an n-dimensional real vector space. I know determinant, and then this is a good one. I've gotten that down, n-dimensional real space. I was really thrown off by this when I started taking this course. The Rn. Printable symbol sheet, cheat sheet, that's kind of cool. Maybe I'll ask for that later, but let's go back to the lesson here. So closure under scalar, so commutativity, associativity, meaning that u plus v plus w is the same as u plus v plus w. Parentheses can be moved. Oh. The additive identity. This means there exists a zero vector such that that contained in the vector space such that the vector plus the zero vector equals the vector. The additive inverse, for every vector within a vector space, there exists a negative version of that vector. Closure under scalar multiplication, that the vector times some constant is going to be contained in, is an element of the vector space. Then distributive laws, associative, scalar multiplication, etc. The space should behave like ordinary vectors in an n-dimensional space. You can add, subtract them, etc. What is a subspace? A subspace is a subset of vectors of a vector space itself that itself is a vector space. So it's just a smaller version of a vector space. To test whether W is a subset of V, you want to see, okay, this is important now. Subspace test. So I'm going to save this for my extension. The zero vector is in W. W is closed under addition. W is closed under scalar multiplication. If all three hold, it's a subspace. All right, let's do some examples. Is this a subspace of two-dimensional space? W equals xy, an xy matrix that is an element of r squared, y equals 2x. So is there a zero vector? X equals 0, y equals 0 is true. Oh, so I need to be able to make this true with 0 and 0. Interesting. I guess that also means, does it pass through the origin? I think that's what it means. I'll confirm that later. Is it closed under addition? Y sub 1 equals 2x sub 1, and y2 equals 2x sub 2. Then y1 plus y2 equals 2, x sub 1 plus x2. That works. This is an interesting proof. Oh. It's a really interesting proof. I'm not sure exactly why that's true, but let's see. All right. Then closed under scalar multiplication. Is this closed under scalar multiplication? I have x comma 2x as this point. I see they just plugged in 2x for the y value. Oh, that's where they got this. They could pick 2 points, oh, an x1, y1, and an x2, y2. So it is a subspace. It's a line through the origin in two-dimensional space. Cool. So this next one's not a subspace. Let's see why. It's the set of all vectors xy contained in R squared with x greater than or equal to 0, a subspace. So the 0 vector is contained within W, the subspace. Yes. It's contained within a two-dimensional space. Is it closed under addition? The sum of two vectors with x greater than or equal to 0 still has x greater than or equal to 0. Yeah, if I add two positive vectors, it'll stay positive. But then scalar multiplication is a no. If I put this, -1 times this number. All right, this doesn't fully make sense to me. I'm going to make a note to myself. That's for my app that I'm building with all these screenshots that are sort of my notes as I go. So it's not a subspace. I'm going to really have to think on this one. I could just highlight it and go explain this further. Let's go for the guided examples. Oh, I did that. Practice problems. Okay. So now they have number one. This is my favorite part of the course always. I like doing practice problems. Active learning is the best kind of learning, not just passively reading stuff. So V equals R, a three-dimensional space. Vector space is the set W. XYZ, here's the X plus Y plus Z equals 0, a subspace. So the three tests I need to do are 0 vector. The 0 vector exists. I have 0 plus 0 plus 0 equals 0. Check. Then I do close under addition. I guess I want to see more examples of ones that don't work with, or they don't have a 0 vector, or don't have are not closed under addition. Of what? Of vector spaces that are not subspaces because they are not closed under addition or do not have a 0 vector. So I can compare. That'll give me help. Examples really help explain these concepts for me, at least. And it's always good to ask ChatGPT for examples. Even as a tutor, just giving students example problems is always really helpful. It's sort of the whole crux of the app I'm building, to use AI to turn your notes into good spaced repetition practice. So is the set of all vectors a subspace? I think it's closed under addition because I could go x1 plus y1 plus z1 and x, I think this is how we set it up, plus y2 plus z2 equals 0. And you could add these up. So I'm just combining these two equations. Zero plus 0 is 0. I think it's all good. And then is it what is the last thing? Scalar multiplication. I think it is. Like 3, yeah. Cx1 plus y1 plus z1. And it still is true. So I'm going to say yes for this. Let P2 be the set of polynomials of degree 2 or less. Is the set of all polynomials P of X a subspace of P2 with P of 1 equals 0 a subspace? Okay, so if P of 1 equals 0, if a polynomial of degree 2 is of the form, this is number 2 here, ax squared plus bx plus c equals, in this case, it's going to be I'll just say like equals d or something like that. Actually, I should say equals 0 because c is a constant. I can just do c minus d would be the new variable. So I set that as the polynomial. And I know that p of 1 equals 0. So if p of 1 equals 0, that means it becomes a 1 squared. I'm plugging in x equals 1 plus b 1 plus. So a plus b plus c. Is that a subspace? I think so. It's the same thing as this one. So I'm going to say yes again. And then it asks, is the set of all 2 by 2 invertible matrices a subspace of the space of all 2 by 2 matrices? Oh, God, that's a tricky one. So let's see. Fails because it lacks the 0 vector. X plus y equals 1. 0 plus 0 does not equal 1. Okay, cool. I need to pass the origin. Not close under addition. I guess this means is an integer. Not closed under scalar multiplication. Lines on either side mean is less than or equal to 1. X1 and Y1 both have a normal of 1 or a magnitude of 1 inside the set, but this has a normal of 2, root 2. So the x vector plus the y vector equals that. What is norm? All right, this is getting a little intense, a little confusing. To be expected, though. That's fine. It's the magnitude, okay. So the x vector is equal to, it's all magnitudes less than or equal to 1. I'll be honest, that does not make sense. I have to review that more. The Euclidean norm is you do basically Pythagorean, but with multiple variables, distance formula. A vector is 3, 4. The magnitude of that vector is 5. Interesting. Okay, I'm going to have to review that more. Let's go ahead and ask it for... Hopefully it gets the right problems. It's practice problems 1 through 3. think it's all yes, but I feel like I'm wrong. So practice problem 1 is the zero vector in W. Yeah, it can pass through 0. Closed under addition. Cool. So the sum of, so U plus V is that. Sum of the components is that. It's still in W. Cool. Closed under scalar multiplication. X, Y, Z equals 0. Yeah, C times 0 equals 0. That's what I thought. Cool. Yes, it's a subspace. The 0 polynomial P of X equals 0. P of 1 equals 0. Yep. It's closed under addition. P of 1 plus Q of 1 equals 0. Yep. So this is about combining functions being the same as those individual functions added up together. Okay. Oh, I get this one above now. Okay, I'm going to explain this whole norm craziness. So it fails because of addition because basically this seems like the main way it would fail under addition. I should ask for other ways it could fail under addition. So it contains the 0 vector. It's closed under scalar multiplication. It's not closed under addition. So the reason is because if I take the individual x and y vectors, they each have a norm of 1, so it's 1 plus 1, it's 2. But if I combine them, if I take the magnitude of the x plus y vector, it has a norm of root 2. Those are not equal. That makes sense. To me, at least. Maybe it doesn't make sense to anyone viewing this, but I'm taking this course for myself and just hoping to share insights with y'all. And have y'all help me use the AI better and learn linear algebra better. It's been fun. Still is fun. So this one's tricky. So the 0 matrix. Oh, this is the set of all invertible. That's the issue. If you plug in the 0 matrix, it's not invertible. So it does not contain the 0 vector. Closed under addition, if I have A and B, A plus B equals the 0 matrix, but they are both invertible. A plus B, though, is not invertible, so it's not closed under addition. So if you add them up separately versus add them up together, yeah. Got it. Okay. Time for the practice quiz, mini test, whatever they call it from this unit. So concept quiz. Define a vector space in one sentence. I'll try not to look at my notes. A vector space is the space that contains a vector and all of its possible additions and scalar multiplications, something like that. Did I define vector space above? I know they did. Vector space. Okay. What is a vector space? A vector space over a set of real numbers is a set of objects that can have vector addition and vector scalar multiplication. And they satisfy all those axioms. Okay, so I basically got that right. It's about a vector addition and scalar multiplication. Now, I really wish there was a way to pin this note that has the main lesson plan. So, number 2, what 3 properties must a subset satisfy to be a subspace? I just did this. Let's see if I remember. So, to be a subspace, it has to contain the 0 vector. There has to be commutative addition and scalar multiplication. True or false, the set of all vectors in R squared with norm less than or equal to 1 is a subspace. No, because of the vector addition thing. Okay, so give me answers to the 3 concept quiz questions. This is nice. We got into the lesson in closer to 30 minutes than an hour. Let's see what this one looks like. Oh, this is loading. Cool. I'll do some more checking up there. Let's make sure I was on track with these problems in the practice quiz, though. Oh, it's here. Yeah, it's false. I kind of saw this. This is the unit disk. All points inside are on the unit circle. Oh, yeah, that's what the magnitude equal 1. But there are fail points because I can go 1, 1. Yeah, this is right. What 3 properties must a subset satisfy to be a subspace? Contain the 0 vector, closed under vector addition. I'm going to write that down because I forget to say closed. Closed under vector addition. Closed under vector addition / scalar multiplication. I feel like linear algebra, someone posted this, but there's a lot of rote memorization. I feel like it would really help if a teacher just jammed into your head every class multiple times what these 3 properties must be to satisfy being a subspace, what the 10 rules are. Like, there's a lot of memorization that you just have to jam into your head. I'll get it down eventually. Be closed under vector addition. Be closed under scalar multiplication. Yeah. This is the subspace test, the minimum required to inherit all vector space properties from the larger space. I'm going to screenshot this. This is a pretty good question. True or false, the set of all vectors in the two-dimensional space with, oh wait, I already did that one. That's what you get when you go opposite. Vector space is a set of vectors over a field like that equipped with vector addition and scalar multiplication that satisfies a list of axioms, closure, associativity, identity, etc., allowing vectors to be combined and scaled while staying in the space. Great. All right, let's look at what this other tab is trying to say for this lesson. Consider the following tasks to reinforce your learning. Exercise 1, exercise 2. I skipped all this though, but you start with the 0 vectors, see if 0 works. So take 2 arbitrary elements from your set and add them, verify that the resulting vector still satisfies the defining property of the set. They phrase things much more clearly in O3 Mini High, I've noticed that. Multiply an arbitrary element of this set by an arbitrary scalar. I think when they say arbitrary, you do still have to set a variable for it, so that you can't just pick 2 every time, because that might just be a coincidence that it works. So a specific subspace of R3 has to have the 0 vector, be closed under addition, and closed under scalar multiplication, which can all be proven algebraically. It really helped when I asked for some null examples. Eight axioms. All right, I want to do these exercises. Let W1 equal that, and let the two-dimensional space equal that. Show that W1 is a subspace of R squared. So 0 minus 0, that works. I can add these together. X1 and X2, Y1 and Y2, those work. And I think if I multiply it, it'll also work. Define W2 as the set of all polynomials of mostly degree 3. Verify whether W2 is a subspace. This is just like what I did. So a lot of these questions they're making are the exact same. Check if the 0 vector is in W3. And then x squared plus y squared equals z squared. And then examine closure properties. Answer exercise 3 in the interactive exercises. I like that they gave a challenge one. Give me a couple of challenging. What questions should I be asking after this lesson to ensure mastery, true mastery? We need to determine whether this set is a subspace of three-dimensional space. You check for the 0 vector, yep. closure under addition. I think that's going to be true. So I pick a U and a V. Oh, it does not. Let's see that here. So I have a U, 1 plus 0 equals 1. I have a V, 0 plus 1 equals 1. I compute their sum. If you check closure under scalar multiplication, you'll find that if U equals XYZ, it is an element of W3 and A. This is a crazy note. I'm going to have to screenshot this. Check closure under scalar multiplication, you'll find that U is 3 points contained in the subspace, and A is an element of all real numbers. A times x squared plus A times y squared equals to A squared, x squared plus y squared. Yeah. Which is equal to A squared z squared, so it's equal to AZ squared. This shows that A times the U vector is contained in W3. However, since closure under addition fails, W3 cannot be a subspace. Oh, that was the scalar multiplication check. Explain more why addition fails. Why closure under addition fails. For that, but wouldn't fail for x plus y plus z equals 0. What is a vector space really? What makes a set of things vector-like? Answer these, don't just give me the questions. Answer those questions. And then, yeah, oh, this is cool. Build a map. Vectors could be arrows in space. So a vector space is any set of objects. So they're not even saying set of vectors, set of objects. I think I would have gotten a point a little off for that. So that's why polynomials or functions work. So don't think of those as vectors. They're objects, but they have, you can add them together, scale them by numbers, and all these rules apply. This is a deep concept, I feel like, in math. It's still gelling for me, but nice, well phrased. And then why do we care about subspaces? Stable piece of a structure within a larger space. This, a matrix times a vector equals 0. The solution is a subspace because it's closed, linear, and contains 0. Cool. This is a crazy point. Why subspaces show us why about, okay. Why must a subspace contain the 0 vector? It's the identity element for addition. You can't form additive inverses. This is a good question, man. These are tough questions. If they had any of these questions on a test, I would struggle. Dang, they're just dropping definitions like crazy here. It's a linear equation. I didn't say x squared plus y squared plus z squared. I'm not sure this is right. Let's ask Claude. Wow, they're using this as a playground example. This is crazy. How do subspaces appear naturally in other topics? The null space, column space, row space, image and kernel, and linear transformations. Almost vector spaces. Zero vector must be in three-dimensional space. So they got the same thing that it's not there. Oh, what? I literally just misread the problem. X squared plus y squared equals z squared. Yeah, no crap that you can't add them. Wow, that's embarrassing. I see now. Okay, I just misread that. That's cool. So these are different symbols. I'm going to write these symbols down. We got this fancy Q is rationals. And Z right here, integers. They never teach you this, but it's a whole different language, math. The field matters. The scalars must themselves form a field. No, because integers aren't closed under scalar multiplication by all scalars in Z. That's an interesting point. I'm going to screenshot it. What do subspaces look like in high dimensions? Well, hyperplanes to the origin, general linear flats. How do subspaces show up in the real world? Okay, computer graphics. All transformations are linear. Data science, machine learning. PCA. What is PCA? Principal component analysis. All right, this is too intense. Anyways, I got through this lesson. I feel decent about it. I'm going to have to jam on the vocabulary. Two main takeaways today were about asking for examples, specifically null examples of rules, and also asking for questions I should be asking is going to always make my head explode and give me a lot to think about. So thanks for tuning in. I'll be back tomorrow. Should be at the regular time at 8:30 a.m., hopefully, assuming that I'm not a zombie in the morning completely. And yeah, keep learning. Stay learning.